Setbacks along the way. No doubt, we've all gone through at least a little bit of a learning curve. There's been plenty of setbacks along the way. Whether we've had our tools lost or stolen or broken, or some new innovative approach hits the market, or a particular piece of equipment hits the market and we've got to purchase or learn new techniques or purchase new tools. All of those things cause us setbacks, and many of those are unavoidable. However, it's not always the case. Sometimes our setbacks really are avoidable. They happen here in our head, and that's one of those things that's really difficult for us to deal with. Misconceptions and hurdles, no matter what the refrigerant is, or what the device or manufactured equipment or situation on an install may be, those are always prevalent. We always have some sort of setback because of the way that we're perceiving something or the way that we're trying to work out the end game. However, when it comes to refrigerants, there haven't been any setbacks with any refrigerant to date as widely prevalent as what we had with 410A in the early 2000s. In fact, there was a lot of people when manufacturers started mass producing units with our 410A that said, I'm never going to work with it. Well, now why would they possibly say that? Did they have firsthand experience that led them to believe that it wasn't good, it didn't work right? Well, here we are almost a couple of decades later, and 410A is still being used. So it can't be the fact that it didn't work right or that nobody wanted to work with it. It was some sort of a mental barrier that these folks had. This was one of them, high pressures. No doubt R410A had higher pressures than what the previous refrigerant of R22 had. When you were working with R410A, it was pretty overwhelming to think of working on equipment, residentially like commercially speaking, that could potentially have up to 600 psi on the high side. Now, operating pressures normally weren't that high. They were somewhere around 300 psi, maybe a little bit north of there, but they could potentially go up to 600 psi. And how do we know that? That's where your safety cutout was. Your high pressure cutout on a 410A system is somewhere around 600 psi. Now, your internal pressure relief on the compressor or your discharge relief is going to be somewhere around 610, usually about 10 psi off from what the high side is. Not every manufacturer is exactly the same. So that was a little overwhelming. And if you remember, the gauges that first came out didn't make it any better. They were dial style gauges, and they had pink inner dials, and the hoses that came down off of the manifold were so thick that even on a 90-degree day, if you undid them from the manifold, they would still hang there stiff as a board and would not flop out and straighten out. So that was pretty difficult to think about. You're sitting there thinking about, okay, these gauges are having to contain this refrigerant with that much pressure. That's a real big mental barrier for me. And what happens if it sprays me? What happens if it gets on my hands and my eyes? And all of those things were valid concerns, but very rarely did the people that had those concerns actually have that happen to them. Oftentimes, it's a story that they heard. Somebody somewhere that they knew had something go sideways, and normally it was because they weren't using best practices, right? We talk about refrigerants in several different senses. Their pressure ranges, some high, some low. Their flammability ratings, some high, some low. Their corrosiveness, their hygroscopic qualities for water absorption or moisture absorption. All of those things are valid concerns, but you got to think of it this way. Those are only a concern if the refrigerant gets out of its containment. If you're doing things according to best practices, using low loss fittings, using the appropriate gauge sets and hoses, and taking your time and connecting and disconnecting things the way that you should, most of the time you're not going to have any issues. Most of the time you're not going to be surrounding yourself with people that have issues. And so don't let that be a barrier. Pressures are only a means to get the temperature, right? On a pressure temperature chart, you have to have the pressure in order to get the temperature, and you have to have the temperature in order to do your superheat or subcooling, right? You have to have the temperature on the inner dial of that gauge so that you can use that temperature and the temperature on the line set, do your subtraction, and that'll tell you your active superheat or subcooling right now. Those things are very important. Okay, but don't think of it as a danger. It's just a means to the end. So pressures really, when you look at it, and this is not the greatest example, I admit that, but it's the only real easy one to explain. When you look at the pressure differential between R22 and 410A, roughly 30 to 70% higher pressures with 410A, which is why it requires a different metering device and things like that. But those guys that are in refrigeration and automotive can actually relate a little bit, because when they went from R12 to 134A, the pressure differential and compression ratio difference was roughly the same. It was very, very close. Now, your end result pressures were not as high with the 134A as they are with 410A, but again, we talked about that. Pressures are just a means to the end, and they shouldn't be that scary to you, especially if you're using your best practices approach. Now, this was another mental block, different tools. Manufacturers did not help this. Wholesalers did not help this, because in the beginning, everything was different. R410A required a complete change out of the system, the coil, the line set, the condensing unit. In addition to that, there were so many different kinds of tools. If you go into a wholesale house, they might have had 2 to 3 different aisles of just 410A equipment. And so really, if you were around at that time, you didn't know if you had to have special tools or you didn't have to have special tools. All you really knew was the oil was different and the pressures were different. And based on that limited knowledge, oftentimes we did not question whether or not we had to have special tools. We just bought them. Make the irony a little bit more prevalent. R410A's color is called rose. If you look at rose, rose is more of a pink, almost like a Pepto-Bismol color than anything. So all of these tools were color coded for the 410A so that you could tell the difference from a regular tool and a 410A tool. And so these tools were pink, which was, before pink was cool, really. You're after the 90s when we had the hot pink, and you're before the pink ribbons for the breast cancer and becoming cool in that nature. So you're right in that middle range there, where you had all of these pink tools, and it was kind of interesting. Now, not all the tools were required, even though we may have bought them. And I'm going to tell you right now that I fell for that game. I wasn't sure what I needed, what I didn't need, so I had a whole set of tools that were different for R410A. Now, gauges were dedicated. You had a dial style gauge. There really wasn't a whole lot of options for the digital gauges. There was a couple of options out there. Robinair had one. You had to buy different keys for different refrigerants, and there were some issues on the computer side of it. It would drain your battery very, very quickly. So I also bought that. It didn't pan out to be very, very good for me. But the gauges, the dial style gauges, those were very specific. You had a set of gauges for R410A only. And now you're starting to see, or you have seen for a while, one set of gauges that has both refrigerants on it. That's one interesting thing that the industry has done is they've upped the pressure rating minimums on hoses and gauges to meet the minimums for R410A. So you see these refrigerant gauges with R410A and R22 both on that inner dial for their PT chart. So you've got a temperature rating that's suitable for those refrigerants, but the pressure rating is also suitable. So you're able to use it on either or for those refrigerants with safety because you know, they're listed for that. So the gauges were special. The gauges still are special, right? You have to be able to accommodate the pressure range and the oils that are being used as well. The recovery machine. Now, if you go back to the early 2000s, recovery machines were not like they are today. The recovery machines were very special. So if you had 134A, you had a special recovery machine for that. If you had R22, there was a special recovery machine for that. If you had 410A, there was a special recovery machine for that. And boy, they were as heavy as a truck full of rocks. I still remember the company that I worked for when we were switching over from R22 to 410A and we had both of those recovery machines. For one, the recovery machines used to be much more expensive than they are right now. You go back 20 years, $1,000 20 years ago was more than $1,000 is today, and they were particular to the refrigerant, and they were super, super heavy. So if you needed one for a different refrigerant than what you had, you'd have to go check one out, and he'd wheel it out, no kidding, on a two-wheel dolly because it was that heavy, and oftentimes you had to have somebody help you put it in the back of the van. The old recovery machines were, depending on the manufacturer, between 70 and 90 pounds each. Part of that is because of a different makeup. Most of the outside of those and the components internally were all made of steel, so that added weight to it. But they also had a reservoir tank inside of them, which is why they had a purge factor on there and things of that nature. So the current recovery machines are not as special. When you get into the current recovery machines, they have dropped all the steel components. Most of those are durable plastic type material, and then they've lost the reservoir tank, so now it's literally just a pump inside of their compressor that's inside of there that's pulling the refrigerant out of the system and pumping it directly into a recovery cylinder. So you lost a ton of weight by getting rid of that reservoir tank. But another thing that did, it lost your little purge switch that used to be on there, and with losing that purge switch, that means we lost the reservoir tank. So that made our refrigerant recovery machines a little bit less specific. So now you can use one recovery machine, if it's a modern one, on oodles and oodles of different refrigerants that are out there. The compression ratio, remember, that's in that one compressor is not nearly as important in a recovery machine as it is, say, in a condensing unit, because you're not using it for refrigeration. You're just wanting to draw the refrigerant out and put it into a recovery machine. So, and not to mention, the older recovery machines had a way for you to pull the vapor out first, and then after the vapor was pulled out, then you would actually switch over and start pulling out the liquid. And the newer recovery machines are much quicker than the old ones because they want you to draw liquid out right from the beginning. And in fact, they use the liquid refrigerant going through that compressor as a coolant to keep that compressor from going into thermal overload. So there is a difference in the recovery machines on the older ones, but currently the difference is just not there anymore. The vacuum pumps, believe it or not, back in the day, they had specialized vacuum pumps just for 410A. And that was kind of a farce, right? The vacuum pump actually is not special or particular to any refrigerant. All it's doing is drawing the system down into a negative pressure or into a vacuum after the refrigerant has been removed. So it's not specific to a refrigerant. The only thing that's really specific about a vacuum pump is the style that you're wanting to use. If you have a bigger system, you would maybe have a bigger vacuum pump smaller system, of course, you would have a smaller vacuum pump. Those things are specific, but the refrigerant certainly is not. The nitrogen bleeders were never specific to a refrigerant. That's science. When you're using a set of torches in order to put together a line set or to braze in a high side or a low side or any of the above, a nitrogen bleeder is necessary because you're going to purge nitrogen through the system in small amounts, somewhere around 1 to 2 psi. You're not building up pressure. It's a really small amount because all you want to do is displace the oxygen. You want to get rid of the oxidation that happens inside of that line set. If you've ever brazed a line set before, then you've probably seen that chalky black stuff, the sooty stuff that gets on the outside of the fittings. Well, that stuff happens on the inside too. And because of that, what happens is once you release the refrigerant and this starts to flow, if you've got all of that oxidation inside of the line set, it simply sweeps it to the smallest part of the line set and plugs it up, which is usually going to be say possibly your metering device, your pressure drop in the coil, your restriction tubes, your header pipe, things like that, may even get swept into the compressor and get stopped up in there, especially if you've got unloaders or things like that. So nitrogen bleeder became more prevalent with R410A because R410A is a much better detergent than previous refrigerants that we've used, and so it was really good at cleaning the inside of that line set and sweeping all that stuff to the smaller parts of the line set. So with that in mind, you ask yourself, do I have to have a nitrogen bleeder, a low pressure regulator, or something of that nature? No, you don't have to in some instances. Okay, the reason that people use a nitrogen bleeder or a low pressure regulator is because the high pressure regulators, once you get down below 50, 45, somewhere in there PSI, they don't regulate the same. The regular nitrogen regulators for the high pressure go up to 2000 PSI or so. Those regulators are designed for high pressure, and once the pressure gets low enough inside of that tank that it can no longer press on the regulator's diaphragm the way that it should, it doesn't keep a stable flow. So trying to get down to 1 or 2 psi on a high pressure regulator, it doesn't always work. Sometimes it does. So I don't want to tell you have to have a nitrogen bleeder, but to control the flow of nitrogen through that system, it is so much easier, so much more stable to do so. And obviously, you wouldn't be sitting through these classes if I was going to give you shortcuts to do this or that and not really know if you were doing it the right way. So yes, you could do it either way. I just think it's more professional and stable to use an actual nitrogen bleeder during the brazing process. Okay, another early on belief is you can't top off the R410A, right? So if it leaks out a little bit, you can't just go back and put refrigerant in it and bring it up to charge like you could with R22. That was the original belief, and much of that belief came from the fact that R410A is a two-part blend. And they're not lying, but the difference between R410A and most other refrigerant blends, like for instance 427 or 407C or something like that, is R410A is a near azeotropic blend, which means we've taken more than one refrigerant, put them together, and as we've put those together, they have formed a bond that makes them almost completely molecularly joined. Now they do have a few qualities of their former single components, but their temperature glide is less than 0.3 of a degree, and their fractionation is nearly zil. So there's no special charging procedures. There's really no fractionation to speak of, no separation to speak of. So there really isn't any huge discrepancies in the way that you would charge this versus something else. Now, that's one of those things that was a real barrier for a long time, because in the beginning, if you lost any charge in the system, it was treated as though it was like any other Zeotropic blend, which the difference between near azeotropic, like 410A, and zeotropic would be like taking oil and water and dirt and putting it all in a beaker and stirring it up. The only time that it's all mixed up is while you're doing the stirring. You stop stirring and it all separates out, and at that point you don't have a blended refrigerant anymore. So if you had the water start to evaporate out of that beaker, well, then you don't have the same mixture anymore, right? You have more oil and dirt than you do water. So it's not going to act the same. That was the thought with 410A. Okay, but they don't separate. 410A doesn't separate like other refrigerants. If you take a zeotropic refrigerant, it acts exactly like the beaker of water, oil, and dirt. A zeotropic refrigerant, like 407C, has a high temperature glide, a high fractionation rate, so if it leaks, it could leak at an uneven rate and lose some of the individual components, which then would change the mixture of the overall refrigerant. And therefore, the safest bet is to pull it all out and charge back as new. With 410A, that was the belief. But because it's near azeotropic, the science tells us that's not true. And so currently, the way that it stands is if there's still charge in there, much like its predecessor R22, you can, of course, bring it up to charge with your superheat or subcooling and your temperature drop across the coil, making sure that your blower speed is set properly. You can do all that stuff, and there won't be really any danger to the refrigerant itself, but we all know that the danger comes from running low on refrigerant in the first place. So you have to find the refrigerant leak. Otherwise, you're just going to leak the stuff out that you just put in there. And for one thing, practicality purposes, tells us it isn't going to get any cheaper. And plus, they're going to be without cooling and dehumidification, again, like they were the time that you got out there to do this. And in the meantime, it's going to start to do damage to the compressor because low on refrigerant means low on oil recirculation. So if you're not circulating that oil through the compressor, think of a car. You ever been around a car that's had a lifter that's been ticking? Tick, 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 tick. So annoying, isn't it? I'm sure that brought you back to an earlier car that maybe you had in high school or something like that. Well, I'll tell you, those cars with that little lifter tick, they run forever. They never completely break down, so it's always hard to cut the chain and get a new car. The same thing happens with the air conditioning systems, it seems like. Now, obviously, that is an opinion of mine. That's not a fact, but it seems like the trouble air conditioning systems last forever. And they just limp along, and by the time the customer actually changes it out, they probably have spent enough in repairs that they could have changed it out more than once and been better off efficiency-wise and long-term. So the topping it off portion was not long-lived, but that was a huge mental barrier in the beginning. Now here's some other setbacks that we've had, and these are just kind of fun ones. I'm going to remove my picture off here so that way you can actually look at what I've got written up here. When you look at the rules of thumb, now the rules of thumb are not really rules at all. I'm not sure where some of these came from, but I remember learning every single one of these throughout my career. Right? This is the first one. Feeling for sweat on the line set. Back in the old days, in fact, back in the 90s when I was originally getting into the industry, I still remember several people never checking superheat or subcooling. They would simply stick their mitts on the line set and feel for sweat. And once that refrigerant flashed, they would consider it properly charged. So you'd be looking for what they call the sweaty soda can effect. However, that hasn't been accurate in decades. That was maybe close on the old low SEER R22 units, but ever since the SEER ratings have gone up and we've changed refrigerants into the 410A field, that's just no longer accurate. What happens is on the higher SEER units, the 410A ones, you can have a very high temperature range and that line set still may not sweat if it's charged properly. And that's a hard one to unlearn. I tell you, when I'm going out working with guys in the field, one of the things that I still have trouble with and struggle with, if somebody's got a problem with their air condition, the first thing I look at as I'm walking by is sweat on the line set. And I know that's not right. But it's very difficult to unlearn those habits. All of these are actually fairly difficult to unlearn. The second one, the condenser temperature minus the ambient outside temperature. That was also one that was used on the low SEER R22 units. And depending on who you talk to, and this was actually in a couple of periodicals as well, depending on who you talk to and what you were working on, you would measure the temperature coming out of the top of the condensing unit and the temperature outside away from the condensing unit, knowing that heat travels from warmest to coolest. So you had to have a certain temperature difference in order to have a good heat exchange from that condenser to the outside air. And that temperature range was between 25 degrees and 35 degrees, depending on, again, your SEER rating and who you talked to or got the information from. Now, to be honest with you, I don't know if that was ever actually accurate. It may have been. I've never seen anything from a manufacturer that asks for that. But I do know a lot of people have used that, and there are still some guys out there that try to use that. But 410A displaces more heat, so that temperature that's coming out of there is not going to be the same as what it was with the R22 units, and you're running with more efficiency, and the compression ratio is also lower, which means more or less heat is coming off the compressor, so you're not going to have the compressor heat that's coming up through there. So that plays a factor as well. Now the next one is a favorite even still today. Never been accurate. 10 degrees of superheat on everything. That has never been accurate. That's a very specific load range when you think about it, right? 10 degrees of superheat. Well, what is superheat? Superheat is the amount of refrigerant that's in the coil, basically is what you're measuring, because after the refrigerant is all boiled off, it can continue to still absorb heat, and that's really what you're measuring there. The difference between the saturation temperature and the actual temperature of the refrigerant. How much heat has it absorbed past that point? Well, think about it. You've got slide rules, you've got manufacturer specs, you've got all kinds of things to check the superheat. If it's just 10 degrees on everything, you'd never need any of that stuff. But if you'll use a slide rule, I'll give you an example. A slide rule asks you to set up in steps 1 and 2 your wet bulb temperature outside and your inside, and your dry bulb temperature outside. Step 1, if you simply slid your wet bulb temperature over to 68 degrees wet bulb for the inside of the home, which is really not all that cool if it's dehumidifying properly. But if your outside temperature, which would be your next setting, was 85, 68 degrees on your wet bulb inside, 85 degrees outside gives you 19 degrees of superheat that you're looking for. And that's on an average day. That's on a day that you go out that the customer may have had their windows open for a little while and just shut them before you got there. So it still might be a little bit warm and clammy because it hasn't had time to dehumidify. So that right there should point out that 10 degrees superheat on everything has never been accurate. It's a very specific load range. And then another one that I hear from guys that's actually a little bit frustrating from time to time is they'll give you a specific gauge pressure over the phone. Hey, my system's running at 295 PSI on the high side. What should I be looking for? Well, I can't tell you. If your blower speed is set up properly and you're checking your temp drop and your temp drop is not right, say it's too low or it's too high, okay, in those instances, you've got to make adjustments on your charge. And the only way that you can do that is by actually checking your superheat or your subcooling. Superheat is always done on the low side of the system with a fixed metering device, and subcooling is always done on the high side of the system with an expansion valve only. Now, the other thing you got to keep in mind is the whole idea behind an expansion valve is to get the same subcool or superheat all the time. So you may have to check the superheat on an expansion valve system, but it's not for the purpose of charge. It's for the purpose of making sure the expansion valve is set properly and also operating properly. So that's kind of a loaded question when I get that on the phone. And so those are just a few of the rules of thumb. There's all kinds of rules of thumb that are out there that are even more pressing than many of these. So keep that in mind as we go forward through everything, and know that there is no such thing as a rule of thumb. It's only a setback right here that eventually someday will be very difficult for you to unlearn.